capability. And this multi-tenant capability has been in DB2 since the early 90s. Now I know there's been competitive technology within the last week or so that's been making a lot of noise about new multi-tenancy capabilities and the first multi-tenant database in the industry. But we've had this technology since the early 90s. So we've got a lot of experience with them. We really understand how that technology works, where it works well, and we're really building out on top of those capabilities. So you can actually deploy databases into the system. Again, it fits into a DevOps model where you just have a simple interface. That interface allows you to define a database name at the simplest level, the database size, and it will then go off and deploy that database into a cluster. So let's take this one level deeper. So when we talk about consolidation, we actually have, again, two levels of consolidation. You can actually have multiple clusters within a system. You can actually have up to 12 clusters defined in a single pure data system. So you've got that level of consolidation, and you can actually then define multiple databases per cluster. As Arden talked about earlier, you can actually define more than 100 databases into a single system. So let me talk now about some of the optimizations we've done, and why these optimizations help you with availability and performance characteristics. First, again, people have heard about the compression technology in DB2, and Arden talked about this earlier. We've just released this adaptive compression. The adaptive compression technology provides us a mechanism that gets extremely high levels of compression. So we've seen compression rates of up to 10x. So what's important about compression technology is the compression is not just compressing data on disk. We actually keep the data compressed in memory as well. So when you compress the data, we actually stuffing more and more rows into a data page. The data pages are sitting in memory. And we've actually got a significant amount of memory on the system. And the memory is in a hierarchy itself. So each server, each member in the cluster, in the database cluster, has its own local buffer pool, so its own cache of pages. So when you go to try to read a page, the first thing we do is we go to that local buffer pool. The more memory, the more data you fit into memory, the less IR we do. Also, we have a second tier buffer pool, which is a global buffer pool. And that global buffer pool is used for your buffer coherency. So in a shared cluster, you've got to have a way of coordinating access to pages that are being looked at across that cluster. So the second use of memory is, again, this global buffer pool. And with the compression technology, we're able to put more pages into, and more rows into that system as well. So we've got two tiers of memory utilization. By putting more rows into the buffer pool, local buffer pool, we reduce network traffic to the global buffer pool, and we reduce I/O traffic. So we're doing a lot of optimizations around our memory utilization. When it comes to the communication protocol between the systems, we're using something called remote direct memory access, or RDMA. And what RDMA is it's a very, very low latency mechanism which allows you to directly touch memory from system to system. Now we're using this mechanism for things like lock requests. So if you want to make a lock request for a specific row in a data page, there's about a 10 to 15 microsecond round trip time to actually execute that lock request. I'll give you another example of how we use RDMA, and this is for paging validation. So if you have a data page, and that data page is shared across the cluster, and one of the members is going to update that page and do a commit of the data on that page, what will happen is that page gets written back to the global buffer pool, again through an RDMA protocol. But then we actually have to invalidate all the other pages, all the other copies of that page across the cluster. And the way this is done is using the RDMA protocol, we'll touch a single bit on that data page on all members. And when we touch that bit, the latency of that operation is very low. But more importantly, we don't take an interrupt on that target system. We don't use the CPU on that target system, and we don't go into the kernel. So this is not only very efficient from a latency perspective, but it's also very efficient from a compute utilization perspective of the other system. So that's another example of the optimizations we have. So I've gone through compression, memory optimization, network optimization, and now I'll talk about SSD. So what we've done with solid-state disk is we're actually using solid-state disk in the storage tier. And the solid-state disk is being actually stored in. It's not a cache. We're only putting the data in one place. It either resides on a solid-state disk or it resides on a hard disk drive. And we have an algorithm that's sitting there that's looking at the frequency of access of the data pages, and it's dynamically moving that data back and forth between solid-state disk and hard disk. So the most frequently accessed data gets moved to solid-state disk. If data is not accessed as frequently, it gets moved to hard disk drives. Also, all writes, when we make a write, are go to that solid-state disk first. So we get all the write-off capability of solid-state disk. We get all the write rate secure data benefits of solid-state disk. And again, as that data is accessed infrequently or frequently, I would say it should move to SSD technology. So these are the sorts of optimizations that we've actually built into the system. From an innovation and acceleration capability, this gives you the capability of deploying systems very rapidly. It allows you to use the built-in database patterns we have to actually deploy databases. So it's a very, very simple mechanism again. But you can customize these patterns as well. So you can customize a pattern, do things like change the database size, whatever you think is necessary for your workload. And you can capture these patterns and then have these patterns as a standard that you can deploy in your enterprise. We also support the capability of cloning databases from a database backup. So you can have a pattern that says, okay, I want to base this pattern based on what I've already captured in the backup of a previous database. So we have many different ways you can actually accelerate the deployment of these systems. Now, a database without an application is a fairly useless entity. Just the same as an application without data is fairly useless as well. So what we really want to do is combine the concepts and the logic and all the capabilities we built into pure data with the capabilities of pure application. So when you're building out a pattern of pure application, you really are building out a pattern that's centered around your application. You're encapsulating the application logic and you're encapsulating the logic associated with other components of the application. So HTTP servers, application servers, caching services, queuing services, LDAP directives, whatever you're going to have. And also database components. So you can, on the pure application system, build out this type of pattern and this type of topology and deploy your application and all those components completely on the pure application system. Now, with the database tier on that system, you're using a virtualization technology. It's not using the shared scale architecture. So you're really targeting databases that are either of a lower availability in nature or lower throughput, lower response time. But we've extended that to allow you to marry these two systems together. And as Arvin's talking about, what you can do is actually build out that pattern I just described. You can deploy it onto your pre-application system. You can deploy it as a test pattern. You can run that pattern, test your application out, make sure it's working well, and then say, okay, now I want to put it into production. And when I put it into production, I'm just going to change that pattern this bit to specify that the database is going to be deployed on the pure data transaction system. And you can now deploy that pattern and get deployed across all systems. So not only do we have these pure data systems, but we have a lot of logic that's integrated that's allowing you to use these with the pure application system. From a simplification of the experience perspective, we have a fully integrated monitoring and management infrastructure. This monitoring and management infrastructure is built into the system, but we also have the capability of having SNMP alerts that come out of the machine, so you can capture those and trap those into your enterprise monitoring infrastructure. If you look at the actual management infrastructure, starting with the infrastructure layer, you get a full pictorial representation of the rack. And on that pictorial representation, you see all the components. You see your servers, you see your storage, you see your network. Now what we do is we have alert lights on each of the components, so you can have a green, yellow, or red alert. And if you have, say, a yellow alert, you can drill into that individual component. You can capture the diagnostics, look at what's going on in that system. So let's say you have a yellow alert on the server. You could drill into that server, and you could say, okay, my database is running slow there.